So in this video we are going to discuss the questions which appeared in JRF physical science examination that occurred in June 2017. So let's continue with the first question. The statement is a thermodynamic function G equal U minus ds plus Pb is given in terms of internal energy, temperature, entropy, pressure and volume and the number of particles. So which one of the following relation is true? So for this purpose we need to expand the given thermodynamic potentials and then we will be able to find out the answer. Okay, so let's try to understand this problem. So let me write the given thermodynamic potential, which is basically the Gibbs free energy, that is U minus ds plus Pb. Okay, so we can find a small change in Gibbs free energy dg, that is equal to du minus tds minus sdt plus pdv plus v dp. Okay, so here we will make use of the first law of thermodynamics. So and we are going to replace du by first law of thermodynamics. This is equal to du, that is dq, which is equal to tds, basically du, that is equal to tds minus dw, which is pdv. Okay, so we will make this substitution here in this equation and then we will see that some of the terms will cancel with each other. So du that is equal to tds minus pdv. So this is du basically. Okay, now the remaining terms in the change in Gibbs free energy, so which minus tds minus sdt plus pdv plus v dp. Okay, so from here tds will cancel with tds and then what else, pdv will cancel with pdv. So ultimately we are left with dg, that is equal to minus sdt plus b dp. Okay, so now from this equation we see that, and okay, so in case of an open system, because here one of the option it involves the chemical potential here, so in that situation we can consider the another term that is mu dn basically. Okay, so that we can add here plus mu dn. Okay, so here we will have another term plus mu dn. Okay, now let's try to understand which quantities we can obtain from this equation 1. Okay, so from here we note that S is equal to minus dg by dt if we keep pressure and number of particle constants. So by keeping n and p constant, so S will be how much? So just take a look at this. So this will be 0 when pressure is constant, this will be 0 when pressure, number of particles is constant. Okay, so S will be simply minus dg by dt. Okay, so similarly we can obtain the expression for the volume and the chemical potential. The volume will be from this relationship from equation 1, volume will be how much? Volume will be dg by dp. Volume will be dg by dp by keeping t and n constant, or you can say n and t constant. Okay, similarly mu is equal to dg by dn by keeping other two variables t and p constant. Okay, t and p constant. So now if we compare the option which are given to us, so first option is given to us S is equal to minus dg by dt at n by keeping n and p constant. So therefore that means this is correct. Okay, and what about the okay, so this is wrong because the first one is correct. So v is dg by dp, so this is with the negative sign, so that means this is also wrong. And mu is dg by dn, so here its negative sign is given, so that means this is also wrong. So therefore the only option A, it's correct. So let's continue with the next question. So we are given a gas of photon inside a cavity of volume V. It is in equilibrium at temperature T. Okay, if the temperature of the cavity is changed to 2T, so that means we are having a cavity whose temperature is changing from T to 2T. Okay, now the question is the radiation pressure will change by a factor of. Okay, so we know that in case of a three-dimensional cavity, the radiation pressure inside a cavity. So this is basically a 3D situation. Okay, so the pressure it is proportional to T power 4. So therefore, when temperature is changing from T to 2T, so if we say that the corresponding temperature's pressure is P2, and here it is P1. Okay, so then P2 by P1, this will be equal to T2 upon T1 its power 4, which is nothing but 2T divided by T and its power 4, and this is nothing but it's 16. So therefore correct answer is option B here. Okay, now let's take a look at the next problem. Okay, in a thermodynamic system in equilibrium, each molecule can exist in three possible states with probability, okay, 1 by 2, 1 by 3 and 1 by 6 respectively. The entropy per molecule is given by. So here you need to remember one important relationship that you might have learned in statistical mechanics. It's a relationship that connects the entropy with the probability. Okay, so I'm going to write that equation for you. So the relation that connects the entropy with the probability, that is given as S is equal to minus K. K is a Boltzmann constant. I am not using the suffix V here. Just keep in mind it's a Boltzmann constant. And then summation over I Pi ln Pi, where Pi is simply the probability. Okay, probability. Now we are given three different probabilities. What are those? P1, this is 1 by 2. P2 is given to be 1 by 3 and P3 is 1 by 6. Okay, so now let's try to figure out what is the net entropy for the given situation. So S will be, we will have three different terms corresponding to P1, P2 and P3. So S is equal to minus K P1 ln P1. Okay, so what is P1? That is 1 by 2 ln P1 1 by 2. Okay, plus P2 which is 1 by 3 ln 1 by 3 plus P3 1 by 6 ln P3 which is 1 by 6. Okay, now this can be further rewritten as minus K outside, okay, 1 by 2 ln 1 minus ln 2. Okay, so we are going to expand it basically. So plus 1 by 3 within the bracket ln 1 minus ln 3, sorry, it's 3. Okay, plus the last term 1 by 6 ln 1 minus ln 6. Okay, so ln 1 is 0 as we all know. Okay, so this is basically equal to, so here we will have minus K and this will be 0 and this is also 0 and this is also 0. So minus and minus will become plus. Okay, we are having a one minus here and another minus outside, so that will become plus basically. Okay, so this is equal to K 1 by 2 ln 2 plus 1 by 3 ln 3 plus 1 by 6. Now we are having ln 6, so I'm going to split it into two quantities. So ln 6 is equal to, basically, let me do it roughly here. So ln 6 can be written as ln 2 multiplied by 3. So log of A into B, that is equal to log A plus log B. So this can be written as ln 2 plus ln 3. Okay, the only purpose is that we want to bring this in terms of these quantities. Okay, so 1 by 6 ln 6 is equal to multiply by ln 2 plus ln 3. Okay, now we are going to collect the terms involving same logarithmic. Okay, so this is equal to k. Now ln2 terms we will bring together, so this is equal to 1 by 2 plus 1 by 6. Okay, plus 1 by 6 multiplied by ln2. Okay, now the terms having ln3 common, so plus 1 by 3 plus 1 by 6 ln3. Okay, so after solving this, we obtain that entropy, that is equal to k multiplied by 2 by 3 ln2 plus 1 by 2 ln3. So if you just take a look at the options which are given to us, so it is 2 by 3 kb ln2 plus kb by 2 ln3. So that means C is the correct one. C is correct here. Okay, so let's continue with the next question. The statement is, a box separated by a movable wall has two compartments which are filled by a monatomic gas with adiabatic index which is given to be gamma, that is equal to Cp by Cb. Okay, initially the volumes of the two compartments are equal. Okay, so let's try to draw what is given in the statement. Okay, so we are given a box or which is divided into two equal compartments. Okay, the volume they are given to be same initially. Let's say the initial volume they are V0 and V0 and okay, what the pressures are 3P0 and P0 respectively. So here let's say in this chamber the pressure is 3P0 and here it is P0. Okay, when the wall is allowed to move, so let's call this as our system A. Now the second situation is, what is that? In the situation 2, when this ball it's allowed to move, the final pressure in the two compartments become equal. Okay, now if it's allowed to move, so let's say it will settle at a certain position, and then the pressure inside these two compartments that is equal. Let's say the final pressure is Pf, and then the corresponding volumes are V1 and V2. Okay, let's call this as system B. Okay, now according to the given situation, what we can do is we can write in the final situation or in the final condition the total volume, that is V1 plus V2. The total volume, it's not going to change, it will be always 2V0. Okay, it's merely the in the central wall which is moving basically. Okay, now because here if you just take a look at the options which are given to us, these are in terms of the adiabatic index. So that means a message is clear to us that somehow we have to make use of the adiabatic expansion here. Okay, so assuming that the equation which is valid for the adiabatic expansion, that is Pb power gamma, that is equal to constant. Okay, so we will make use of this result here to solve this problem. Okay, so now for system A, if we apply this PV power gamma is equal to constant, so for the initial situation, which is this one, the initial pressure is 3P0. Okay, 3P0, and what is the volume, corresponding volume? It is V0. Okay, and Pb power gamma, that is equal to the final pressure in this part, the left part. Okay, that is Pf here. Okay, so that is equal to Pf, and then corresponding volume which is B1, we have written B1 power gamma. Okay, so from here we can find B1 in terms of the given parameter, which will be B1 will be simply just rearrange these equations. So this will be 3P0 divided by Pf and then multiply by V0 power gamma, and because we are having B1 power gamma, so if we are removing the power from the B1, so it will become 1 by gamma on the other side. Okay, so let's call this as equation 2. Okay, now similarly for the second part. Okay, so if we call this as the system A and this is system B. Now for the second part of the system, for system B, sorry, in the beginning I mentioned these as system A and system B separately, but we will call the left part as system A and the right part as the system B. Okay, please note it. Okay, for system B, again we are going to apply the equation 2 here. So for system B, the relationship that is valid, that is PV power gamma, that is P naught B naught power gamma, that is equal to PF, the final pressure, and multiply by B2 power gamma. So this will give us, this implies B2 will be P naught B naught power gamma divided by PF and its power 1 by gamma. Let's call this as equation 3. Okay, now these three equations, that is 1, 2 and 3, 1, 2 and 3, collectively they imply that B1 plus B2, that is equal to 2V naught. Okay, now simply add B1 and B2 from by using equation 2 and 3. Okay, so if you do that, so this will be equal to 3 P naught B naught power gamma divided by PF and its power 1 by gamma, that is B1 plus B2. So B2 is equation 3. So plus P naught V naught power gamma divided by PF and its power 1 by gamma. Okay, so therefore 2V naught turns out to be equal to, therefore after solving or rearranging the terms, 2V naught will be 3P naught by PF and its power 1 by gamma, and B naught power gamma power 1 by gamma, so that will be simply V naught. Okay, plus the second term, same way we will separate the terms, P naught by PF power 1 by gamma and multiply by V naught. Okay, so from here we can take PF outside. So if you take PF on the left hand side, so that will give us PF power 1 by gamma, that is equal to 1 by 2. Okay, and in the bracket we will have 3p naught, PF we have taken outside, so this will be 3p naught, B naught and B naught will cancel with each other, so we will be left with 3p naught power 1 by gamma. Okay, plus P naught power 1 by gamma. Okay, let's move to the next page. I think I will not be able to finish it here. Okay, so now PF power 1 by gamma, this is equal to P naught power 1 by gamma. So I have taken P naught outside. Okay, so P naught power 1 by gamma multiply by 3 power 1 by gamma plus 1 divided by 2. Okay, or what you can do is you can write simply PF is equal to now we need to multiply by gamma on both sides, so that will be equal to P naught divided by 2 power gamma and then multiply by 1 plus 3 power 1 by gamma and its power gamma. Okay, so let's take a look at that, which option is correct. Okay, so here if you just take a look at option A, it's not correct. Option B is also not correct. So option D is also not correct. But here also in the option, in the way option C is written, it's also not correct here. So basically it should be 1 by 2 power gamma here. So then option C will become correct here. So let's take a look at the next problem. The statement is the single particle energy level of a non-interacting three-dimensional isotopic system. So we are given a non-interacting three-dimensional system which is labeled by momentum k are proportional to k cube. Okay, so it's given that the energy of the particle it's proportional to k cube. Now we are asked the we are supposed to find the ratio of the average pressure to the average energy at a fixed temperature. Okay, so we can handle this problem by by finding the expression for the partition function. Okay, and then by knowing the average value of the pressure and energy with the help of the partition function. Okay, so basically let's continue with the things which are given to us. So we are given that energy for the particle it's proportional to k cube. Okay, and we can write it to be proportional to momentum because k and p they are proportional to each other, so this is proportional to p cube basically. Okay, and the reason is that because p this is equal to h cut k, so p and k they are directly connected with each other. Okay, so therefore we can say that E that is equal to a p cube, where a is a constant. Okay, so let's call this as our equation 1. Okay, now P and the average energy they can be calculated as below. So P it's connected to the Helmholtz free energy with the this relation P that is equal to minus dA by dV. Okay, where A is the Helmholtz free energy. Okay, so A it's connected with the partition function by this relationship A minus KT ln Z, where K is a Boltzmann constant and Z is the partition function. Okay, now further the another quantity that we need to find out it is the average energy. So average energy it is connected to the partition function with this relation A E minus that is equal to minus curly beta of ln Z. Okay, so let's call these two equation as equation 2. So therefore if somehow we are able to find out the partition function, then we can quickly find out the ratio between the P and E. Okay, it's not the ratio between P and E is basically the energy density. Okay, so basically we need to find, after finding the average energy, we need to find the energy divided by the volume, so that will give us the energy density, which is written like small e. Okay, so now let's try to find out the partition function for this system. So the partition function is given as Z that is equal to 1 by h cube. Okay, 1 by h cube and then integral exponential minus beta e dqp dq q. Okay, and this is equal to, so this integral over the q that will give us the v, so we can write it as v upon h cube, and then the limits of integration exponential minus beta e exponential minus beta e is ap cube. Okay, and then dqp, so 4 pi p square dp. Okay, and this is further equal to 4 pi b upon h cube 0 to infinity p square exponential minus beta a p cube dp. So let's call this as equation 3. Okay, so now if you just take a look at the integral that we are having, it's not a general integral that we usually encounter while dealing with the problem of the partition function. Okay, so that means we have to somehow solve it by making some sort of substitution, and the substitution that we are going to make here is that we are going to put this beta ap cube with the certain another variable. So if we say that let y that is equal to beta a p cube. Okay, so that dy that is equal to 3 beta a p square dp. Okay, so from here we will find the value of p square dp because we need it here in the integral. Okay, so from here p square dp, that is equal to 1 divided by 3 beta a and dy. And another important point that we have to note here is that as p goes to 0, what happened to by also goes to 0, and as p goes to infinity, y also goes to infinity. So therefore the limit of integration, they will not change. Okay, so therefore with this information the partition function can be rewritten as z, that is equal to 4 pi b upon h cube 0 to infinity, then exponential minus by that new substitution, and then p square dp, so which is equal to 1 upon 3 beta a and dy. Okay, so this integral, the exponential function, if you just take a look at this will turn out to be unity. Okay, so let's see it. 0 to infinity exponential minus y dy, and that will be exponential minus by upon minus 1, and from 0 to infinity, and this will turn out to be unity basically. Okay, so that means the partition function comes out to be equal to partition function z, that is equal to 4 pi b upon 3 beta h cube a, and multiply by 1, which is the value of the integral, definite integral. Okay, so this is our partition function. So let me call this as equation 4. Okay, now we will make use of the definition of the pressure and energy to evaluate these two quantities. Okay, so let's move to the next page. So the pressure is, as I said in the beginning, so pressure, that is equal to kT time curly b of ln z. Okay, so this is equal to kT curly b of ln 4 pi b upon 3 beta h cube a. Okay, so that means that is equal to kT and then the differential with respect to volume. Okay, so kT in then 1 by x, the differential of ln this quantity, that will be 1 divided by this quantity, so that will give us 3 beta h cube a upon 4 pi b, and then its differential again, so then multiply by differential of the term which is inside the logarithmic. Okay, so that will be and differential with respect to volume, so that will give us 4 pi upon 3 beta h cube a. Okay, so 4 pi will cancel with 4 pi, and this term will cancel with this one. So ultimately we are simply left with kT by b, kT divided by volume, and that is equal to 1 upon beta b. So that is the pressure basically. Okay, so let me call this as equation, let me check. Okay, equation 4 I have already written, so this is our equation 5. Okay, now the average value of energy. Now average energy. Okay, so as I said earlier, so average energy E, that is minus curly beta minus curly beta of ln z, so that is minus curly beta of ln 4 pi b upon 3 beta h cube a. Okay, and this is further equal to minus again 1 by x. Okay, so that will be minus of 3 beta h cube a upon 4 pi b, and then differential with respect to beta. Okay, so the constant terms will remain as it is, 4 pi b upon 3 h cube a, and then differential of 1 by beta, so that will be minus 1 upon beta square. Okay, so this 4 pi b and 4 pi b will cancel, 3 h cube a will cancel, 3 h cube a, so beta here and minus will become plus, so this is equal to 1 by beta. This is 1 by beta, and this is our equation 6. Okay, now we have to find out the energy density E, that is equal to energy divided by volume, and that will be equal to 1 upon beta V. So let's call this as equation 7. So now therefore what is asking the questions, we are supposed to find the ratio between the P by E. Okay, so that is nothing but 1 upon beta V multiplied by beta V upon 1, and that is equal to unity. So that's the answer basically. So let's check the options. Okay, so therefore option C is correct here. So let's take a look at the next question. So the question is, the Hamiltonian for 3 Icing spins S0, S1, S2 taking value of plus minus 1 is given as by this expression. So basically this is the question from the Icing model in one dimension with free boundary conditions. Okay, so if this system is in equilibrium at certain temperature T, the average energy of the system in terms of beta is, okay, so we have to find the average energy, and this we can do by simply working out the expression for the partition function, and then from there we can find the expression for the average energy for the system. Okay, so let's try to solve this problem. So we are given a system of 3 spins. So I'm going to summarize the different microstates here, and the corresponding energy for this different microstates. The spins are S0, S1 and S2, and let the corresponding energy, that is H here, and which is given by this expression, okay, which is given to us. Let's call this as equation 1 here. Okay, so now because it's given that these spins, they can take either a value of plus 1 or minus 1. So plus 1 mean, let's take that a spin pointing in the upper direction, we assign a value of plus 1 here, and when spin it's pointing in the downward direction, we assign a value of minus 1 here. Okay, so the various possibilities could be, so these are all spins, they are pointing in the upward direction. Okay, so this is a situation when all 3 spins, they are pointing in the upward direction. Okay, and same way we can write the expression for the other possibilities, minus 1, plus 1, plus 1, and then 1, minus 1, and then plus 1. Okay, then the next option 1, and the third one is pointing in the downward direction. Okay, now the second the other option 2 pointing in the downward direction, okay, and 1 pointing in the upper direction. Okay, so minus 1, plus 1, minus 1. So this is 1 basically. Okay, minus 1, plus 1, minus 1, and then 1, minus 1, minus 1, and all spins pointing in the downward direction. Let's count how many options are 2, 4, 6 and 8. Yes, there should be 8. Okay, so now I will work out the corresponding energy for the first 2 cases, and same way we can find the energy for the rest of the cases. Okay, so here the Hamiltonian is given to be H, that is equal to minus J S0 multiplied by S1 plus S2, and this is equal to minus J S0 S1 plus S0 S2. Okay, now let's take a look at the first case where all the spins, they are pointing in the upward direction. So that means S0, S1 and S2, they are having positive value of unity. Okay, so this will be the corresponding interaction energy will be minus J S0 and S1, 1 multiplied by 1, okay, plus 1 multiplied by plus 1. So 1 plus 1, that will give us 2, and multiply by minus J, so corresponding interaction energy will be minus 2J. So we will write here minus 2J. Okay, similarly for the second case, this one, okay, let's call this as H1. Okay, now for the second case, which I'm calling as H2, the corresponding interaction energy will be minus J S0 S1. So S0 and S1, so they will give minus 1. Okay, minus 1 plus S0 S2, minus 1 multiplied by plus 1, again another minus 1, minus 1. Okay, so minus 1, minus 1, minus 2, and then multiply by minus J, so that will give us plus 2J. Okay, so this way we can work out the corresponding interaction energy for the rest of the cases. So here for the second case, this is plus 2j, and then for this case it will be 0 0 0 0, and for this case the energy will be 2j, and for this case the energy will be minus 2j. Okay, so now here I'm going to summarize these results here. So H1, that is equal to minus 2j, and corresponding degenesis G1, that is equal to 2, because here we have obtained 2 times the energy of minus 2j, so that's why the corresponding degenesis is 2 here. Okay, and now what is the energy H2 plus 2j? It's also occurring 2 times, 1 2. Okay, so corresponding degenesis is 2, and how many times 0 have occurred? It's 4 times. So let's call this as H3, and this is 0, and the corresponding degenesis is G3, that is equal to 4. Okay, so now we can write the partition function. So the partition function is Z, that is equal to sum over all the states Gi exponential minus beta Hi. So here we have basically these are total 8 microstates, but because of degenesis, so we will have only 3. Okay, 3 cases. So 1 to 3, or in principle you can take the summation from 1 to 8, and then you have to write the each term separately, and then by summing we will obtain the same result. Okay, so the partition function will be G1, which is 2 exponential minus beta multiplied by minus 2j, so that will give you 2 exponential 2 beta j. Okay, now the second case, for this case, so degenesis is 2 exponential minus 2 beta j plus G3, which is 4 exponential minus beta 0, so that will give us the 1. Okay, so that's the partition function, and this can be rewritten as 4 as it is, and then here if we just take 2 outside from this expression, inside we will have exponential 2 beta j plus exponential minus 2 beta j, and that will be basically 2 cos hyperbolic 2 beta j, and that 2 multiplied by this 2, that will become 4 cos hyperbolic 2 beta j. So here in the inside the bracket we will be left with only cos hyperbolic 2 beta j plus 1. Okay, so that is the partition function. Okay, now when the partition function is known to us, then we can quickly determine the average energy. So let's move to the second page. So the partition function that we just obtained, that is Z, that is equal to 4 multiplied by cos hyperbolic 2 beta j plus 1. Okay, so let me check what number I have. This is 1, so let me call this as equation 1. Now how we can determine the average energy U, that is equal to minus curly beta of ln z, so that means minus curly beta of logarithmic of 4 multiplied by cos hyperbolic 2 beta j plus 1. Okay, so its differential, that is equal to minus 1 upon 4 cos hyperbolic 2 beta j plus 1. Okay, and then again its differential with respect to beta. Okay, so if you differentiate this quantity, so this will be basically 4 and then sine hyperbolic 2 beta j, and then differential of this quantity, so with respect to beta, so it will be 2j. Okay, so 4 will cancel with 4. Okay, and this is equal to minus 2j sine hyperbolic 2 beta j divided by cos hyperbolic 2 beta j plus 1. So that is the average energy for the given system. Okay, so let's check the options that are given to us. So if you compare the results that we have obtained, so option D is the correct one here. Okay, so let's take a look at the next problem. So it's a problem which is related to the random variable, which is discussed usually in both mathematical physics as well as in statistical mechanics also. So that's why I'm considering this problem here. So the problem is the random variable x, which ranges from -infinity to infinity, it is distributed according to the normal distribution which is given to us. Okay, the probability density of the random variable y is equal to x square is. Okay, so let's continue with the problem. So we are given the normal distribution which is px, that is equal to 1 upon under root 2 pi sigma square, and it's under root exponential minus x square upon, actually okay, it was minus x square, it's minus x square basically, minus x square upon 2 sigma square. Okay, so let's call this as equation 1. Okay, now we will apply the normalization condition here. So that means applying the normalization condition, which means -infinity to infinity px dx, and that should be equal to unity. Okay, so that means so we are going to substitute the value of px here. Okay, so that is 1 upon under root 2 pi sigma square, and then the variable -infinity to infinity exponential minus x square upon 2 sigma square dx, that is equal to unity. Okay, this can be further rewritten as 1 upon under 2 pi sigma square, and then 2 times 0 to infinity. So we are making this transformation because here we have to match the result with one of the options. So here the variation it's given from 0 to infinity. So we are going to bring in another variable which is y here in terms of x square. Okay, so that's why we are doing this change here. So exponential minus x square upon 2 sigma square dx, that is equal to unity. Okay, so let's call this as equation 2. Okay, now here we are going to make a substitution for x square. We will put x square equal to y, which implies 2x dx, that is equal to dy, or this further implies that 2 dx. So because we are having here 2 and then dx, so 2 dx, that will be equal to dy upon x, or which is further equal to 2 dx. This is further equal to dy upon under root y. So because x square is equal to y, so x will be under root y. Okay, now further what are the limits? Okay, so as x goes to 0, okay, y also goes to 0, and as x goes to infinity, y also goes to infinity. So that means limits of integration, they will not change. So with this transformation, equation 2 reduces to 1 upon under root 2 pi sigma square, and then 0 to infinity exponential minus y upon 2 sigma square, and then dy upon under root y, and that is equal to unity. Okay, or we can further rewrite this as 0 to infinity 1 divided by under root 2 pi sigma square by exponential minus y upon 2 sigma square dy, that is equal to unity. Okay, or this can be written as p by dy from 0 to infinity, and that is equal to unity. So therefore the probability density in y is given by, so therefore probability density in y is given by py, that is equal to 1 upon under root 2 pi sigma square y square exponential minus y upon 2 sigma square. Okay, and with the limits which are given by y, it's lying between 0 to infinity. Okay, so therefore the correct option is which one? This is the A, exponential 1 upon 2 pi sigma square. Not A also. Okay, it's by, not y square. Sorry. So with this it's minus y upon 2 sigma square. Yes, this is A. So therefore A is correct here. So let's continue with the last question. The question is, a random variable n obeys Poisson statistics. The probability of finding n is equal to 0 is 10 power minus 6. The expectation value of n is close to, so we have to find the correct option. So we know that from Poisson statistics, the probability is given by probability p n, that is equal to e power minus average n, then average n power n divided by n factorial. Okay, so here this is basically expectation value of n, which is we have to find this value. So this is also written as n bar, and for the random walk problem, if you remember, this is equal to np basically. Okay, this is the expectation value of n. Okay, this is also called as n is also called number of success. Okay, so now what we are given is, for n is equal to 0, we are given that the probability, the corresponding probability, this is equal to 10 power minus 6. Okay, so we have to simply plug in this value in this equation. If we call this as equation 1, and this result which is given to us as 2, so therefore p of 0 that is equal to e power minus expectation value of n, and then n expectation value of n power n, which is 0. Okay, and then n factorial, which is 0 factorial. So 0 factorial, that will give us unity. So n power 0, that will also give us unity. So that means this is equal to 10 power minus 6. Okay, so therefore e power minus n, that is equal to 10 power minus 6. Okay, so taking a logarithmic on both sides, so we obtain that minus expectation value of n, that is equal to ln 10 power minus 6. Okay, so this can be solved easily. So that means minus n, that is equal to minus 6 ln 10. Okay, so minus and minus, that will cancel with each other. So expectation value of n will be 6 multiplied by ln 10, which is 2.303. So if you multiply these two numbers, we obtain 13.8 basically, and that's almost close to 14. Okay, so therefore A is the correct option here.